Hello, I am Jaydeep. I am from CSEB section, and the topic which I have selected for this concept video is outline the VI characteristics of PN junction diode for reverse bias. PN junction diode. Semiconductors are materials whose conductivity lies between conductors and insulators. Semiconductors are classified as intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors are further classified as N-type and P-type semiconductors. The p-n junction is formed between the p-type and the n-type semiconductors. In this session, let us know more about the p-n junction. So, coming about the p-n junction is formed between the extrinsic semiconductors, which are classified as n-type and p-type. So, these two type of semiconductors are joined and are fused to form a p-n junction. What is p-n junction? A p-n junction is an interface or a boundary between two semiconductor materials, namely the p-type and the n-type, inside a semiconductor. Inside semiconductor, the p-n junction is created by the method of doping. So the p-n junction is formed between the p-type semiconductor and n-type semiconductor. So these are two different types of semiconductors which are doped by the method of doping to form a p-n junction. Formation of p-n junction. As we know, if we use different semiconducting materials to make a p-n junction, there will be a grain boundary that would inhibit the movement of electrons from one side to the other side by scattering the electrons and holes, and thus we use the process of doping. So, the different semiconducting materials to make a p-n junction, there will be a gain boundary that would inhibit the movement of electrons from one side to the other side by scattering the electrons and holes, and thus we use the process of doping. We will understand the process of doping with the help of this example. Let us consider a thin p-type silicon semiconductor sheet. If we add a small amount of pentavalent impurity to this, a part of p-type silicon will get converted into n-type silicon. So if a thin p-type silicon semiconductor sheet is taken and added a small amount of pentavalent impurity, so to the p-type semiconductor, we are adding the pentavalent impurity. A part of the p-type silicon will converted into n-type silicon. So if we add the pentavalent impurity to the p-type silicon, then it will be conducted into n-type silicon. Unbiased p-n junction. So in this diagram, we can see the unbiased p-n junction. So here we have a p-type material and we have n-type material. In between that, we have yellow color shaded region, which is the depletion region, and we can see the charges, minus charge and positive charge in the depletion region, and there are empty holes in the p-type material. So we can see these empty p holes, and here in the n-type material we have free electrons. So this is the p-n junction, and the symbol for the p-n junction is, here we have the symbol where the arrow is marked in the way. So this is unbiased p-n junction. The meaning of the unbiased is, here we have p-n junction diode, but it is not connected to any external supply or any source. So that's why it's called as unbiased p-n junction. Also, when an electron diffuses from the n side to the p side, an ionized donor is left between on the n side, which is immobile. As the process goes on, a layer of positive charge is developed on the n side of the junction. Similarly, when hole goes from p side to the n side, an ionized acceptor is left behind on the p side. Thus, it is the formation of the layer of negative charge on the p side of the junction. This region of positive charge and negative charge on the either side of junction is termed as the depletion region. So, as we know that in the p type we have the holes and in the n type we have the electrons. So these electrons are free electrons and the holes are, we have holes on p side. So the p in the p side holes goes from p side to the n side. So as a result, the negative charge is generated in the p side material, whereas in the n type inside of the semiconducting material we have free electrons. So these free electrons goes to the p side, which makes the positive charges generated in the n type inside of the semiconductor. So as a result, the negative charges are generated at the p side and the positive charges are generated at n side. So these negative and positive ions are collected at the one side, which is called as depletion region, where it forms as a barrier to the movement of the holes and electrons from one and other sides. Due to the positive space charge region on the either side of the junction, an electric field with the direction from a positive charge towards the negative charge is developed. Due to this electric field, an electron on the p side of the junction moves to the n side of the junction. This motion is termed as a drift. Here, we see that the direction of the drift current is opposite to that of the diffusion current. So as a result, the positive charges on the either side of the junction and electric field is in the direction of the positive charge towards the negative charge is developed. So as a result of the movement of the holes from the p side to the n side and electrons from the n side to the p side, so the ions are generated which are formed as a depletion region. So at that time, the positive space charges region on the either side of the junction, the electric field is formed in the direction of the positive charges moving from the p side. So as a result, electric field is generated. An electron on the p side of the junction moves to the n side of the junction. This motion is termed as the drift. So as a result of the depletion region, so the p side of the junction moves to the n side of the junction. As a result, due to this motion, it's called as the drift. Here we see that the direction of the drift current is opposite to the direction of the diffusion current. Biasing condition for PN junction diode. There are two operating regions in the PN junction diode, P-type and N-type. So in the PN junction diode, we have two operating regions. One is P-type and another one is N-type. So let's see the biasing conditions for PN junction diode. There are three biasing conditions for PN junction diode, and this is based on the voltage applied. So the based on the voltage applied to the PN junction diode, the biasing conditions are of three types. First one is zero bias, which means no external voltage is applied to the PN junction diode. So coming to the zero bias, so in the zero bias we have the voltage is not applied to the PN junction diode. So the PN junction diode is left as it is and it is not connected to any external voltage source. Next, coming to the forward bias, the positive terminal of the voltage potential is connected to the P type while the negative terminal is connected to the N type. So coming to the forward bias, the positive terminal of the voltage potential is connected to the P type while the negative terminal is connected to the N type. So in the name itself says that forward bias. In the forward bias, the P type, which is positive, which contains holes, is connected to the P side of the, which is connected to the positive terminal, which is of the voltage source, and N type, which has free electrons, is connected to the negative terminal of the voltage supply. So we have Light terminals are connected to each other. So positive terminal of the voltage is connected to the P side, which is positive of the junction, and the negative terminal of the voltage, which is which it is connected to the junction negative, which is N type. So here we have both positive is connected to positive and negative is connected to negative. In this condition, we call the biasing as the forward biasing. So another type of biasing is there, which is reverse bias. The negative terminal of the voltage potential is connected to the P type and the positive connected it to the N type. So we have seen the forward bias. Now coming to the reverse bias, the P type junction P type is connected to the negative terminal of the voltage supply, and the N type of the PN junction diode is connected to the positive terminal of the voltage supply. Here we have, unlike terminals are connected to one another. So in this we have the P type of the junction, which is positive, is connected to the negative terminal of the voltage supply. So as a result, it has unlike terminals which are connected. And similarly, the N type, which has free electrons, which is negative charge, is connected to the positive terminal of the voltage supply. As a result, the forward biasing is formed, and circuit is forward biased circuit of the PN junction. So with this, we have completed all the three different types of biasings. And let us remember that zero biasing is the condition where the junction, PN junction, is not connected to the voltage supply. So it's remain constant. And coming to the forward bias, in the forward bias, the P type of the semi PN junction diode is connected to the positive terminal of the voltage supply, and the negative terminal of the voltage supply is connected to the N-type semiconductor, which is of negative charge. So in this we have same terminals connected to one another. So in that we have forward biasing is formed between the PN junction and the voltage supply. And coming to the reverse bias, the P type of the PN junction diode is connected to the negative terminal of the voltage supply, and the negative N type, which is of the negative charge, is connected to the positive terminal of the voltage supply. So as a result, the reverse bias is formed between the PN junction and the voltage supply. So coming to the forward bias. So we have in this diagram, we have the forward bias of the PN junction. So here we have N-type material, and here we have P-type material. And we know that in the P-type material we have the holes, and in the N-type material we have the free electrons. So these are positive charges, and here we have negative charges. And these positive charges, which are holes, moves from P-type to the N-type material. As a result, the N-type ions are formed at the P side of the junction. And similarly, in the N type of the semiconductor, as we have the free electrons which moves from N type to the P type, as a result, positive ions are formed on the inside of the PN junction. So as a result, here we have depletion layer formed where these ions are now immobile. As a result, the P holes cannot pass to the N side, and the free electrons of the N type cannot pass to the P side. So to remove this depletion region, we have connected an external supply in the forward bias. So here we have a battery, and it is a positive terminal and it is the negative terminal. So this positive terminal is directly connected to the P side of the PN junction, and this negative terminal of the voltage supply is connected directly to the N side of the PN junction. So as a result, it is positive, and the P side is also positive. So the like charges are connected. like terminals are connected, and here also we can see the negative side of the voltage is connected to the negative side of the PN junction. As a result, here also we can see the negative and negative terminals are connected. So in this condition, we say that it's a forward bias. So in this biasing, we have the positive charges moves from forcefully to the P side, and as a result, and here also we can see the negative charges from the batteries is flows forcefully to the inside. So as a result, the depletion region breaks here. When the P side is connected to the battery positive terminal and the N type of the negative terminal, then the PN junction is said to be forward biased. When the PN junction is forward biased, the built-in electric field at the PN junction and the applied electric field are in the opposite directions. When both the electric fields add up, the resultant electric field has a magnitude lesser than built-in electric field. This result is a less resistive and thinner depletion region. The depletion region's resistance becomes negligible when the applied voltage is large. In silicon, at the voltage of 0.6 volts, the resistance of the depletion region becomes completely negligible and the current flows across it unimpeded. So when the p-type is connected to the battery's positive terminal and the n-type is connected to the negative terminal, the PN junction is said to be in the forward bias. When the PN junction is in forward bias, the built-in electric field at the PN junction and the applied electric field are in the opposite directions. When both the electric field add up, the resultant electric field has a magnitude lesser than the built-in electric field. This results in a less resistive and thinner depletion region. The depletion region becomes negligible when applied voltage is large. In silicon, at the voltage of 0.6 volts, the resistance of the depletion region becomes completely negligible and the current flow across it unimpeded. So coming to the reverse bias, here we have the diagram of the reverse biased PN junction. So here we have the N type and here we have P type where we have the holes and here we have the electrons, and here the depletion region is formed where these are the negative ions and these are the positive ions, and the depletion region is formed in the middle of the PN junction. So here we have the voltage supply, and this is the positive terminal of the battery and this is the negative terminal of the battery, and this negative terminal of the battery is connected directly to the P side of the PN junction, and this positive terminal of the battery is directly connected to the N type of the PN junction. So here no current flows. So at this depletion region no current flows. By the application of the voltage supply in the reverse bias, the current starts flowing. So in this we have negative charge flows to the positive. So this P side positive charges are attracted to this negative terminal of the battery, and here the negative charges are attracted towards the positive terminal of the battery. As a result, the depletion region between the P and N type of the semiconductor material, the depletion region will increases. So in this condition, at the certain voltage, the depletion region suddenly breaks. So this is about the reverse bias. When the p-type is connected to the battery's negative terminal and n-type is connected to the positive side, the p-n junction is reverse biased. In this case, the built-in electric field and the applied electric field are in the same direction. When the two fields are added, the resultant electric field is in the same direction as the built-in electric field, creating a more resistive, thicker depletion region. The depletion region becomes more resistive and thicker if the applied voltage becomes larger. So when the P-type is connected to the battery's negative terminal and the N-type is connected to the positive side, the PN junction is reverse biased. In this case, the built-in electric field and the applied electric field are in the same direction. When the two fields are added, the resultant electric field is in the same direction as the built-in electric field, creating a more resistive, thicker depletion region. The depletion region becomes more resistive and thicker if the applied voltage becomes larger. So coming to the VI characteristics of PN junction. So here we have a graph, and in this graph, the x coordinate axis is the voltage, which is denoted and which is represented by the letter capital V. And in the y axis, we have the y coordinate as the current. And here we have the in the first quadrant, the forward region is formed, and the graph can be seen the curve. The starting of the forward biasing. So when the forward voltage is applied, the graph is at the starting the point is zero, and suddenly at this point it, it suddenly raises. So this point it is called as threshold voltage because at this voltage the voltage as the current has increased. At the starting, if we increase the voltage, there is no change in the current, but at the certain voltage the current has increased exponentially. So this point is called as threshold voltage at which the current starts increasing exponentially. So coming to the reverse bias, condition, we are applying breakdown voltage. So in this also we can see when the voltage is applied, the current at the initial position it is having no change, and suddenly it increases in the negative direction. So this type of voltage is called breakdown voltage. So this is about the reverse region. The characteristics of PN junction diode is curve between the voltage and the current through the circuit. Voltage is taken along the x-axis while the current is taken along the y-axis. The above graph is the VI characteristics curve of the PN junction diode. With the help of the curve, we can understand that there are three regions in which the diode works, and they are zero bias, forward bias, and reverse bias. When the PN junction diode is in zero bias condition, there is no external voltage applied, and this means that the potential barrier at the junction does not allow the flow of the current. So coming to the zero biasing condition, there is no external voltage is applied to the PN junction. As a result, the depletion region is formed between the P side and the N side. So the depletion region is formed between the P side and the N side of the PN junction. So as a result, there is no flow of the current from P side to the N side and vice versa. So the potential barrier at the junction does not allow the flow of the current. So this potential barrier which is the depletion region does not allow the flow of the current in the junction. When the PN junction is in the forward bias condition, the P type is connected to the positive terminal while the N type is connected to the negative terminal of the external voltage. So in the forward bias, the P side of the PN junction is connected to the positive terminal of the battery, and N type is connected to the negative terminal of the external voltage. When the diode is arranged in this manner, there is a reduction in the potential barrier. For silicon diodes, when the voltage is 0.7 volts, and for germanium diodes, when the voltage is 0.3 volts, the potential barrier decreases and there will be a flow of current. So when the diode is arranged in this manner, there is a reduction in the potential barrier. For silicon diode, when the voltage is 0.7 volts, and for the germanium diode, when the voltage is 0.3 volts, the potential barrier decreases and there is a flow of the current. So when the diode is in the forward bias, the current increases slowly and the curve obtained is non-linear, and as the voltage applied to the diode overcomes the potential barrier. Once the diode overcomes the potential barrier, the diode behaves normally and the curve rises sharply as the external voltage increases. and the curve obtained is linear. So when the diode is in the forward bias, the current increases slowly and the curve obtained is non-linear as the voltage applied to the diode overcomes the potential barrier. Once the diode overcomes the potential barrier, the diode behaves normally and the curve rises sharply as the external voltage increases and the curve obtained is linear. When the PN junction is in the negative biased condition, or else we can say reverse biased condition, the P side is connected to the negative terminal while the N type is connected to the positive terminal of the external voltage. This results in the increase in the potential barrier. Reverse saturation current flows in the beginning as minority charges are present in the junction. So when the PN junction diode is in a negative bias condition, the P type is connected to the negative terminal while the N type is connected to the positive terminal of the external voltage. This results in an increase in the potential barrier. Reverse saturation current flows in the beginning as minority charge carriers are present in the junction. When the applied voltage is increased, the minority charges will have increased kinetic energy, which affects the majority charges. This is the stage when the diode breaks down. This may also destroy the diode. So when the applied voltage is increased, the minority charges will have increased kinetic energy, which affects the majority charges. This stage, at this this is the stage when the diode breaks down. This may also destroy the diode. Applications of the PN junction diode. So we have discussed a lot about the PN junction diode. We have discussed about the zero biasing and we have discussed forward and reverse biasing conditions. And we have also discussed about the VI characteristics of the PN junction diode at the forward bias and reverse bias condition. So at last we are coming to the applications of the PN junction diode. PN junction diode can be used as a photodiode as the diode insensitive to the light when the configuration of the diode is reverse biased. It can be used as a solar cell. So the PN junction diode can also be used as a solar cell. In the solar cells where the sunlight is connected and the sun energy is stored in the solar cells, and again this solar energy is converted into the electrical energy. So in this form we can use this PN junction diode. In the solar cells, the PN junction diode is fitted where the solar energy, the energy which is added to the solar cell, and this energy is stored. So when the diode is in forward bias, it is used as a LED lighting applications. So that when the PN junction diode is in the forward bias, it acts like a LED, which is light emitting diode. So generally we use the light emitting diodes in our houses and in the many places we are using the LEDs. So this LEDs works on the principle of the PN junction diode in the forward biasing condition. So in this forward biasing, we are connecting the P-type of the PN junction to the positive terminal and N-type of the PN junction to the negative terminal of the voltage supply. So in this application, in the forward biasing junction, it can be used as a LED. It is used as a rectifier in many electric circuits and as a voltage controlled oscillator in varactors. So these are the applications. I thank the faculty and college for providing me this opportunity to speak on the topic. Thank you.